And we'll see if we can grasp it now. So what we're talking about now, and where did I put my notes? I left it over there. So we have 15E.2, and so it introduces a little bit more information. Okay, but let's look at the question. Okay, we have the position of a particle moving along the x-axis is given by this equation. That's its displacement. And so I've gone ahead straight away and graphed it. Okay, so what you can see is it starts when time is 0, its displacement is 0. All right, when time is like 2.4, its displacement is 0. You know, when time is 5 seconds, its displacement is minus 25. Okay, so we can sort of see those things from it. All right, that's its displacement. Okay, part A says, draw sign diagrams of the particle's acceleration and velocity functions. Okay, so let's leap straight into it. So we know the velocity function is the derivative of s. So I've gone from there to there, simple differentiation, and I need to draw its sign diagram. Okay, Taylor, so what I did is I factorized it, and I've put it as linear factors. Okay, and that's useful because I can see the root is 1 and 5. So I've put them on the x-axis. How else could you do that? Okay, if you're not sure of that process, you just graph this function, g-solve the roots, and draw the sign diagram of the velocity function. Okay, so we can use our calculator to support us. The other really important thing is that when we're talking about kinematics, all our sign diagrams have a line at 0. We don't consider negative values of time. Okay, we only consider positive values of time. So that's the velocity function, it's the derivative of s, and then the acceleration function is the derivative of the velocity function. Now we're not going to try and differentiate it in this form because we don't know how to differentiate things when they're multiplying one another. So instead we go, well this is another way to express the velocity, right? There's two ways to express it. So I'm just going to differentiate this one. And so when I differentiate that, we get 6t, and minus 18, t goes to minus 18, and the 15 disappears. That's our velocity function, our acceleration function. It's the equation of a line. That should be 3, sorry. It's the equation of a line, and its intercept is 3. You put time is 3 in there, you're going to get 0. And so I've drawn its sign diagram because I know it's the equation of a line. It's got positive slope, so it's going from the negative side to the positive side. I can see that it's root 3. So you're going to get so good at it that you can just go straight from there to there. All right, and you'll see when they're polynomials, they all follow this same sort of path anyway. All right, and so the point of that is to say, well, you can also just sketch this function in your calculator, g-solve that root, and draw the sign diagram using your calculator. But we have the sign diagram of the velocity function and the acceleration function. Okay, part A complete. Part B, find the time and position when the particle changes direction. Okay, so the particle changes direction. All right, velocity tells you about its direction. If we have positive velocity, this is by convention. Positive velocity means it's moving to the right, and negative velocity means it's moving to the left. Remember, you learned that in physics. Velocity is a vector quantity, which means it has direction. So if it's positive, we say moving to the right. If it's negative, it's moving to the left. And what that means is it changes direction when time is 1, because it's changed from positive to negative velocity, and it changes direction when time is 5. So let's make that statement. Changes direction when time is 1 and time is 5. Okay? Hey, I'll probably be about 10 more minutes, so you can have 10 minutes if you like.
Oh,
yeah. Thank you very, very much.
Oh,
yes. So changes direction at these 2 points in time. Time is 1, time is 5. Okay, we're getting that from there. We can also observe that on the graph. Okay, have a look at this graph. When time is 1, look what's happening to the displacement. Okay, it goes really far away from the point of origin, and then it starts coming back towards the point of origin. Its displacement starts decreasing. Okay, and then when time is 5, you know, it's really far away from the point of origin, and then it starts coming back towards the point of origin. Okay, in the displacement, that when y is 0, that's the point of origin. Okay, so that's when it changes direction. Now we're asked, what is the position when it changes direction? That means what's its displacement? So that means we need to know what is the displacement when time is 1 and what is the displacement when time is 5. And so you can find that by putting the number 1 into this equation and putting the number 5 into this equation. Now what's so useful about having the graph is you can just get it straight from the graph, okay? When time is 1, the displacement is 7 meters, and when time is 5, the displacement is minus 25 meters. So we have the time and position when it changes direction. Okay, changes direction when the velocity changes from positive to negative. All right, next part. C, when is the particle's speed increasing and velocity increasing? Okay, so here, let's look at where it says important points. An object changes direction if its sign changes in its velocity sign diagram. Now, speed of an object, speed is a little bit different from velocity because speed is a scalar, it doesn't have direction. And so speed is just the magnitude of velocity. All right, so all that's to say is speed doesn't consider direction, negative or positive. Okay? Now let's continue reading that dot point because this is all we need to answer the question. Okay, we don't really need to understand the intricacies of the difference between speed and velocity. It says, if v of t and a of t have the same sign, then speed is increasing. So if they have the same sign, then speed is increasing. So let's look at the velocity sign diagram and the acceleration sign diagram. They're both negative from 1 to 3, aren't they? They both have the same sign from time is 1 to time is 3. The velocity sign diagram is negative between 1 and 5, and the acceleration sign diagram is negative between 0 and 3, and so that they have the same sign over the interval 1 to 3. Okay? So because they have the same sign over that interval, speed is increasing. Speed increasing from 1 to 3, okay? Between 1 and 3, they're both negative. Are they ever both positive? Or does it happen again when they have the same sign? And the answer is yes, okay? After time is 5, they're both positive. Velocity is positive and acceleration is positive. So they have the same sign again when time is larger than 5, okay? And that has no finite stopping point. Okay, so that's speed increasing. When is the velocity increasing? So velocity is increasing when acceleration is positive. Okay, so to answer, that's C part 1 and C part 2. Velocity is increasing when the acceleration is positive, which is when time is greater than or equal to 3. All right, and then the last part, find the displacement when time is 6. Okay, find S of 6 and draw a motion diagram. So when time is 6, the displacement is minus 18. Okay, minus 18. So let's look at all of these points we have. Okay, obviously when time is 0, the displacement is going to be 0. You put 0 in there, you get 0. It starts at 0. We've got S of 1 is 7. We've got S of 5 is minus 25, and we've got S of 6 is minus 18. So let's describe this, like what's happening to this particle, okay? First off, it starts moving to the right until it gets to 7 meters, and then it starts moving back to the left until it gets to minus 25 meters, and then it starts moving to the right, and it's going to keep going that way forever, although we finished our journey at 6 seconds, is what it said. Find S of 6. So to draw a motion diagram, okay, what a motion diagram is it's an axis that has a displacement on it. Now the point furthest to the left that we went was 7 meters. So here's the point of origin. The point furthest to the right we went was 7 meters. The point furthest to the left was minus 25 meters. Okay, and so if we're describing the path of it, well, it started here, okay, that's when time is 0, and then it went to here, and then it changed direction and went to minus 25, and then it changed direction again. Okay, so after 6 seconds, it's 18 meters from the point of origin. Right, that's its displacement. So look, all I've done is map those details onto this axis. When time is 0, the displacement is 0. When time is 1, okay, so here's time is 1, the displacement is 7. Here we have when time is 5, we're at minus 25, and then we change direction, and this is when time is 6. Okay, so that's all good. But we're going to use the motion diagram to figure out how far it's travelled over the first 6 seconds? How far has it travelled? Well, let's have a look. Over this interval, it's travelled 7 metres. Okay? How far has it travelled from here to here?
32.
32 metres. It's 25 metres there, plus 7 metres there. So this interval is 32 metres. And then how far has it travelled from here to here? That's going to be another 7 metres as well. From 25 to 18, that is 7 metres. And so then the total distance that it's travelled, 7 plus 32 plus 7, 46 metres total distance. Okay, so we use a motion diagram to tell us how far it's travelled in total. All right. So the question, like if you look at the past tests, the kinematics questions are pretty similar to this one here. Okay, it's like finding velocity and then recognising that when velocity changes sign, that's when it's changing direction. All right. So let's see how we go with it. Like